Hello everyone, welcome to Dr. Rajesh Biogenesis Chemistry Academy, Hyderabad, Telangana State. In this video, we are going to discuss what is a SN1 reaction, what are the important aspects and what are the possible applications involved in SN1 reaction in variable examinations. So actually SN1 reaction is nothing but unimolecular nucleophilic substitution. Okay, so it is a pure nucleophilic substitution reaction. See, this is nucleophilic substitution reaction and we are saying unimolecular. Okay, so unimolecular means only one molecule is involved. This is one molecule involved in any reaction, that is rate determining step. So it is a nucleophilic substitution, one nucleophile is gets substituted by other nucleophile, the new nucleophile comes from a reagent. So here we are using actually reaction like this. See, I am using a tertiary alkyl halide. Okay, so when tertiary alkyl halide reacts with aqueous potassium hydroxide, now what happens? We are going to get tertiary alcohol, means conversion of alkyl halide to alcohol in presence of aqueous potassium hydroxide is known as SN1 reaction. So you can write directly in the form of general reaction. See, here I am taking R, now this is carbon, this is R dash and this is R double dash and this is X. Next here followed by I am using aqueous potassium hydroxide like this. Now this is nucleophilic in nature. Now halogen is get removed by the nucleophile present in reagent. So this is R dash and this is R double dash. This is replaced by hydroxy group. So what is the role of this X here? That is a nucleophile and hydroxy is also a nucleophile. So substitution of one nucleophile in place of this carbon, which is halogen is connected, that halogen is replaced by a solvent or reagent nucleophile. Okay, so that is known as a nucleophilic substitution reaction. So this is a nucleophile which is simply removed by hydroxy group. Okay, so here mechanism of this reaction is very important one. See here, it is a non-concentric reaction, means it is a multi-step reaction. Okay, now first what I would like to use is here R dash, R double dash and here X is present. And see, this is nucleophilic in nature and this is a electrophilic character, carbon carry electrophilic character. So first step what I would like to use, I want to use a hydroxy group as a nucleophile. See here aqueous potassium hydroxide, this combination always gives nucleophilic character. So when water or polar solvent added to potassium hydroxide, now hydroxy acts as a nucleophile but not as a base. Now hydroxide as a nucleophile, they want to approach over this carbon. Okay, so whenever if this nucleophile want to approach around this carbon, see forward direction there is a dipole repulsion takes place between this newly approaching nucleophile as well as existing nucleophile. So there is no possibility of approaching from this side. So second possibility, now nucleophile want to attack from opposite direction. Opposite direction what happens, see there is a bulky groups are present over here. This is bulkiness of these groups, never give any choice to attack this hydroxy group on this carbon. Now two factors are opposing to attack this reagent nucleophile on this carbon. First one is dipole repulsion between existing nucleophile and reagent nucleophile, and second one is steric crowding around this carbon. So why? Because hydroxy is a nucleophile tend to attack on this carbon. Okay, now finally what happens? Now reagent effect is not observed. Okay, so this is very slow step. So always we know slow step is a rate determining step. So based on that, hydroxy is not involving in slow step. There is no use of using hydroxy in slow step. Why? Because forward dipole repulsion, backward steric crowding is there. So there is no use of using hydroxy group as a reagent in first step. So only tertiary alkyl halide undergoes self ionization. Okay, itself it is undergoes ionization due to presence of this solvent. Okay, and finally slowly halogen is removed. Once if halogen is removed, see there is a formation of a carbocation like this. This is a carbocation which is completely a planar structure. Okay, so this is a trigonal planar possibility is there. Okay, what is the geometry here? Trigonal planar. What is the hybridization of this carbon? Hybridization of this carbon is sp2, trigonal planar. And what about bond angle here? Bond angle is 120 degrees. Now what happens, see here when reagent want to attack on tertiary alkyl halide, now substrate is not supporting, only one molecule involving in slow step but not reagent. Okay, so that's why it is called slow step reaction. and finally only tertiary alkyl halide involved in rate determining step. Finally what happens, see here, now our reagent, what is our reagent? That is hydroxide ion. After ionization of halogen, then this hydroxy ion involved in second step. Okay, now it will attack from above direction, see, it will attack from above direction. At the same way it is also attacked from below direction. This is below direction, dotted line, this is above direction. So if it is attacks from above direction, that will retains its orientation, also called retains its configuration, means you may expect R, R dash, R double dash, and this is hydroxy group. This is retaining configuration, and one more is inverting configuration. It will comes exactly opposite side. This is R dash, R, and one more is R double dash. Okay. So 50% of retention configuration, 50% of inversion, both you will expect. 50% retention, 50% inversion, and finally these two are responsible for getting a racemic mixture. 50% retention, 50% inversion. Due to compensation of these two isomers, you will get a optically inactive isomer. If only one, if you get, that is called optically active. But right now you are getting two isomers of same molecule. So due to compensation, you will get a racemic mixture of optical inactivity. Okay. So here finally we can say one key point in SN1 reaction, that is we are using a tertiary alkyl halide in presence of a solvent. Slow step is a rate determining step. How many steps are involving in this one? Now we know 2 steps are involved. 2 steps are involved here. And what about first step? First step is a rate determining step. Okay, it is a slow step. So rate directly depends only on tertiary alkyl halide. So when rate depends on only tertiary alkyl halide, that's why it is unimolecular reaction. That's why name given as a unimolecular. And in rate determining step only one molecule is involved. So here it is an example of first order reaction. It is an example of first order reaction. 50% retention, 50% inversion products are expected. So we can expect optically inactive isomers are expected here. Okay. And if you select X here, X is equal to halogens are going to be taken. So iodine is preferred as compared to bromine, then followed by chlorine, then followed by fluorine, like this. Effective living group is iodine. And what about reactivity of alkyl halide here? What kind of alkyl halides are going to be used? Okay. So here we can use benzyl is a preferred alkyl halide, benzyl halide. Okay. Next here followed by allyl halide. Next here we can use tertiary, secondary, then followed by primary. So these two are approximately closer to each other. You need to follow this one. Benzyl, allyl, tertiary, secondary, primary, alkyl halides involved in SN1 reaction. And see here it is 2 step. First one is slow step, second one is fast step. So reagent is involving in which step? In SN1 reaction, reagent is involving in slow step or fast step? Reagent is involved in fast step. Okay, reagent involved in fast step. In slow step reagent is not involved. Why? Because dipolar repulsions and steric loading is the factor. And what about intermediate involved in this reaction? And if you consider intermediate is carbocation. Okay, intermediate is carbocation in this reaction. 2-step reaction, intermediate is carbocation. And very important thing in this one is this reaction is accelerated by a polar solvents. Okay, polar solvents will increase the dilution of hydroxy group here. Now if you use any polar solvent such as water will be used here. Okay, next we can use hydrochloric acid, HNO3, H2SO4, like this polar protic solvents are going to be used in SN1 reaction. Okay, and what about the hydroxy group is present? See, the hydroxy group is completely covered with a polar solvent. So that's why this is low nucleophilic. Remember, it is low nucleophilic. Otherwise you can say this particular hydroxy ion is a soft nucleophile. So always remember, the nucleophile involved in SN1 reaction is very softer as compared to nucleophile involved in SN2. Okay, this is a nucleophile but not base. Hydroxy ion which is used in SN1 reaction is nucleophile but not a base. Okay, so in this reaction what happens? See, first after formation of a stable carbocation, you will get a stable carbocation. there is a possibility of existing a rearrangement. Rearrangement is possible in this one. Okay, so means if you get any secondary carbocation have a tendency to give stable carbocation, you will get a tertiary carbocation like this. Reactivity order is tertiary, secondary, primary, and if they have any choice to undergo more stable carbocation, then only they undergo rearrangement reaction. So SN1 reaction purely related to nucleophilic character but not with respect to base. Here we are using hydroxide ion as a, okay, it is a pure nucleophile, it should not be acts as a pure nucleophile but not base. It is not a basic reaction mechanism. Okay, now see, you can take one example and you can clearly understand what kind of reaction it is. See, here I am using a bromine. Now I am using aqueous potassium hydroxide. Can you predict the answer? Retention inversion. Retention means hydroxy place is above direction and one more hydroxy place is below direction. Okay, so this is 1 2 3 clockwise R configuration, 1 2 3 clockwise, that is S configuration. R is 50% and S is also 50%, so it is optically inactive. Racemic mixture, equal amounts of racemic mixture, that is optically inactive. Okay, so I will give some selective questions. You just try to identify which is actively involving in SN1 reaction. See, I am giving some selective molecules in that one which will be actively involved in SN1 reaction. See, I am using a tertiary bromide, tertiary chloride. Now I am using tertiary iodide, option D. Here I am using a bromide. Okay, so which is preferred here? Actively involved in tertiary butyl iodide. Why? Because lesser the electronegativity, ability of leaving character is very high in this one. Okay, one more kind of question. See, which among the following is actively involved in SN1 reaction? Actively involved in SN1. See, this is a bromide. Now I am using nitro group and here I am using iodine. Option C, I am using tertiary butyl bromide. Option D, I am using a vinyl bromide. So which is actively involved? So the preferred answer is, see, this is aryl, it is not benzyl. So answer is tertiary. Remember, this is completely a aryl halide. Aryl halide means it is attaches to sp2. It should not be attached to sp2. Always it should be attached to sp3 carbon itself. Okay. And one more similar type of question. See, which among the following is actively involved in SN1? SN1. Only SN1 reaction I am asking. See, here I am using benzyl and here I am using OCS3. Next, I am taking same benzyl. This is benzyl halide, remains same, and here it is hydroxy group. Next, here followed by I am using a benzyl, same halogen is remain same. Here alkoxy I given. Next, here I given nitro. Now finally see, I given a benzyl. Here benzyl attaches to halogen, that is bromide. Now it is connected to only hydrogen. Now question is, which among the following is very faster in SN1 reaction? Very faster. So for existing very faster reaction, we need to create a more stable carbocation. See, the halogen connected carbon should be a more stable carbocation after ionization. That can be verified only when if you break the bond between carbon and halogen. Suppose see, if you break this bond here, now see, here you will get a carbocation which is stabilized by benzene pi electrons as well as non-bonding. So it is a mesomeric effect. And here also same. Okay. See, remove this halogen, you will get a benzyl cation. All are benzyl. Now these substitutions will decide which will be more stable carbocation. More stable carbocation will give very faster cleavage. Okay. So finally we can write C. Answer B is correct one. Why? Because it is a powerful donor as compared to methoxy. Hydroxy is a powerful donor as compared to methoxy. If you compare the reactivity order, B is very faster in SN1, then followed by A. A is very faster as compared to D. D is very faster as compared to C. What is the reason behind in this one? Reason is these two are donors. It is no donor, no withdrawing group, but right now it is a withdrawing group. So withdrawing groups will decrease rate of reaction. So now one more I will give, same question is remain same. Which among the following is very faster in solvolysis, otherwise SN1 reaction? Okay. So here see, just remember faster in SN1. Which among the following is faster in SN1? See, I am using a allyl bromide now, tertiary bromide. Now see, here isopropyl bromide, now ethyl bromide. Which is very faster? We know very well, that is A. Why? Because every time you need to remember, after breaking carbon halogen bond, we need to confirm that where stable carbocation will exist. See, if you break carbon halogen bond, now you will get a allyl cation, and in this one you will get a tertiary butyl. Now if you break this one, you will get a secondary carbocation, and in this one you will get a primary carbocation. See, this is more stable, means this bond is unstable. So we can break this and we can expect a solvolysis. We can also expect which among the following is effectively solvolysis. We can also expect this kind of questions. Okay. See, one more, same. Which among the following is faster in SN1? Now remember, this is oxygen connected to halogen. Okay. Next, B. Now this is benzyl which is connected to halogen. Next, this is C. It is connected to halogen. Option D, that is tertiary butyl bromide. Which is very faster in solvolysis, or which is very faster in SN1 reaction? Okay. Remember, first, every time whenever if this kind of questions asked in IIT examinations, okay, so especially even for NEET examinations, this kind of questions they are asking. Remember, first, if they ask about solvolysis or if they ask about rate of reaction or fastness of SN1 reaction, first you remove the halogen. Now halogen, if you remove, you will get a carbocation. This carbocation stabilized by non-bonding electrons. Okay, but here if you remove this halogen, this carbocation stabilized by pi electrons, it is benzyl. And what about here? It is allyl. And what about this? It is only tertiary butyl. So see, out of this all, which cation is highly stable, corresponding carbon halogen bond is very weak. We can break that bond easily. So this cation is more stable. Why? Because this carbocation stabilized by non-bonding electrons. Non-bonding electrons are more electron rich as compared to pi. Pi are more electron rich as compared to sigma. This is the order of denticity towards adjacent carbocation. So non-bonding electrons will boost more energy as compared to pi, followed by sigma. So based on that particular criteria, we can say that this is more reactive as compared to B. Okay, B is more reactive as compared to C. C is more reactive as compared to D. Okay, so that is about some sample applications in SN1 reaction. Some more advanced level organic reactions we are going to discuss every day. Try to like, subscribe and comment in comment section. Okay, so similar to SN1 reaction, we can also show how a SN2 reactions are going to play an important role in nucleophilic substitution reactions. Okay, wait for that video and try to support for each and every video. Thank you for watching this class.